Great. So thank you so much, guys. If I can ask you to come, and then we will get started again. This is the last session today. It's a very nice format, the FABRICATE format now. This slightly lightweight, not too many sessions, and so I think it sharpens the mind and allows us to have a more focused discussion. So thank you so much for participating and for being part of all the dialogue. So our last event today is our keynote with Professor Anna Dyson. It's a really great honor to introduce Anna. Anna is the Heinz Professor at Yale School of Architecture and the School of Environment. Here she's founded and leads the Center for Ecosystems in Architecture, an interdisciplinary lab focused on metabolizing energy, water and materials within architecture in radical new ways. She also directs the PhD program in design research and architectural sciences, intersections that of course are incredibly important to our community. Anna has a very long career behind her. In 2007, she created CASE. CASE is the Center for Architecture, Science and Ecology. And in 2007, to think of these intersections is really predictive in its ability. CASE was a collaboration between Rensselaer, is a collaboration between Rensselaer University and SOM, so also here really pioneering how research environments can be shared between academia and practice. Her work at CASE has been prolific in creating new intersections between academic research and industry, driving innovation through direct research and development, but also through the profound reconsideration of how architecture is performed, what technologies it includes, and how these can be appropriated, challenged, and changed through architecture's concurrent social, technological, and environmental agendas. In her practice, she pairs a deep-seated technological focus with a design-driven ethos. This dual focus on what architecture can be and how it is performed through a web of concerns is so specific to her work. It's also through this delicate balancing that she brings with her into her many interdisciplinary collaborations. At Yale, she's continuing this focus on environment, material and energy through establishing new research agendas. Here she's established a new model for the PhD level design research, which received multiple honors for pedagogy, including the award for most innovative academic program from the ACADIA Association and an award of excellence from the United States Green Building Council. She has won awards from esteemed funding bodies such as the National Science Foundation, the Department of Energy, the Environmental Protection Agency, and the UN Environmental Program, as well as private sponsors such as the Bill and Melinda Gates Foundation. Sorry. She holds multiple patents and is exhibited in venues such as MoMA and the World Future Energy Summit. In 2019, her project Ecological Living Module was named the #1 world-changing idea by the UN. So please help me in welcoming Anna Dyson.
I hope I can handle this technology here. Thank you so much, Meta. I have to say, every time I come to Copenhagen, I get really depressed in the beginning because I'm like, why isn't New York more like Copenhagen? Why isn't everywhere now more like Copenhagen? So it's just a really beautiful, beautiful time and such an honor to be in such a gorgeous city and a beautiful place as CETA. So thank you so much for the honor. I'd like to dedicate this lecture to the students that we were just with in Lviv, Ukraine, mostly for the obvious reasons of what's happening today, but also in reference to Jenny Sabin's remarkable presentation earlier today that reminds us that basically all of our artifacts have politics, and we're either creating things that are reinforcing certain types of power dynamics and power structures, or we're creating alternatives. The deeper dive that we're going to do tomorrow with the presentation from my colleague, Monty Pretorius, for solar enclosure water reuse is an example of this, of where we're really motivated by the idea of subverting centralized power structures and offering the alternative for greater agency that is distributed and coupled, not just for humans, but also for extended living ecosystems. So just, that was, by the way, the message board in Lviv. Amazing flourishing of culture in the midst of everything that they're dealing with. It's incredible. So I also want, before I start my talk, I want to give a quick shout out to our UN Global Report that we just launched in the last few months in various venues, such as at COP in Dubai and at the New York Climate Week. It's a partnership with the UN Environment Program and Yale Center for Ecosystems and Architecture. It's the first time that architects have been the primary authors of a UN Global Report. And I think, you know, we won't have time to really do a deep dive on that today, but if you're interested in it, please do download from the QR code here, and I want to invite all of you to potentially think about being part of phase 2. In phase 1, we had there were many more authors than this, but these are the primary authors from 6 different continents and from countries around the world. We were focusing on a few specific regions and then looking at the global context, but we're very, very excited to continue into phase 3 with even more AEC partners and reviewers and collaborators around the world to try and figure out what are the pathways towards radical decarbonization of building materials, and how can we construct the future in ways that are really appropriate to localities and to the sort of hyper-specific conditions of bioclimatic resources that we have around the world. Our report was quite controversial, I would say, especially in some of the incumbent industries like the cement and concrete industry, although we were able to develop new partnerships, such as with Saint-Gobain and Cemex and others as a result of it. So it galvanized discussion. The main key takeaways of the report are something that I think we've heard a lot of today, which is that we absolutely need to avoid unnecessary emissions through a transition to circularity. Circularity, though, has to happen across the life cycle, and it's very, very difficult for us. I think it was mentioned in the last panel. We can't really specify circular materials if they don't exist. There's a growing gap between supply and demand, and we need to enforce the idea of circularity from the inception, from education and throughout the life cycle and across global material supply chains. And that's one of the reasons why we were motivated to do this report. Is we strongly believe that no matter how much participation, collaboration, new ownership models, other things that we galvanize, we won't really be able to do it without cooperative legislation across borders. And not just, you know, slapping carbon taxes on our material producers and disadvantaging the smaller producers, especially in the bio-based fields. The other big takeaway of our report was that we must shift towards regenerative bio-based processes. Now, this certainly does not mean business as usual forestry. In fact, if you read the fine print of our report, we're recommending a net decrease in conventional forestry and an increase in partnering across the forestry, agriculture, and building sectors, and obviously also textiles and other products, in order to manage the carbon cycle of both agriculture and forestry lands, increasing net biodiversity by, in a sense, culling biomass that is byproduct or considered byproduct. So we're going to increase the carbon sequestration and biodiversity of forests and agricultural lands while taking out a massive amount of biomass, avoiding forest fires and inadvertent burning, which is what's happening across the world right now. We burn a lot of that biomass because we cannot basically viably take it off those lands. We don't have ways to upcycle it and to put it into building products. So that's where we come in, the designers and the inventors. We have got to create new material life cycles that are from waste byproducts, and we saw some really interesting strategies earlier today, and I can't wait to see tomorrow and Saturday as well. Sorry, Sunday. Well, actually, Back to the Future with Utsan, and we'll talk about that Back to the Future. So, in general, please go onto our website if you're interested in more information. We predominantly publish, I have to say, these days in the scientific and engineering fields. I don't know why we went down so many rabbit holes at once and tried to climb silos and then tried to connect them, but we're delighted to be invited in a design and architectural forum because obviously at the end of the day our motivations are buildings and architecture. And so I decided that I would sort of respond to the prompt, and the meat of it is going to be, what do we mean by, now I'm using a new term that Philip has given us yesterday, we're learning already to transition towards intradisciplinary. Basically, how are we inside and fully immersed with each other in the development of criteria? What you just saw on the screen was what we used to call the sardine can. That's CASE, which is basically, let's see if I can point, somewhere behind here in one of those Art Deco buildings. It's right here, actually, there's CASE. We were there for 20 years, and you can probably see here why I love Copenhagen so much is because I do love New York City, but it is chaotic, and it has grown without really a plan. One of the things that is interesting about thinking about ecology and ecosystems, though, within the context of a built environment like that, is to think, what is nature and what is living? All of our buildings are living systems, whether or not we think about them as natural or not. And conversely, also, we're extremely inspired by indigenous practices of building that are really copacetic and interfacing with extended ecosystems. And so we're kind of oscillating back and forth a lot with super high-tech technology, trying to understand how to transition the DNA of the built environment towards biocompatible practices, but we're also very, very inspired by what came before. However, I want to point out here that right here, this smokestack from the Lenape settlement there is an indication of what we've been doing for thousands of years. Basically, our built environment is predicated on concentrating fire-burning technologies. Here on the right-hand side, we might have put the bonfire out of the picture. We might not be so conscious of it anymore. We were, as of recently, still having a lot of smokestacks around New York with coal in the basement. But largely, we're trying to decarbonize our grid. We're electrifying our grid, moving towards that. But we still burn energy in order to service the maintenance loads of this right-hand view to the tune of 11,000 megawatts per day. But ultimately, I would say that we are on a direct trajectory from some of the most ancient practices in that we are burning to make, burning to maintain. And we're in this massive revolution in the 21st century, which couldn't be more exciting at the same time as we're in crisis. We are in a bioinformatic revolution right now. We're learning how to make things very differently. Couldn't happen at a more precipitous moment. This is now the same view of New York City right after Hurricane Sandy, or Superstorm Sandy. It wasn't even a hurricane that took all the lights out of here for several weeks. And we can see the brittleness of our built environment here is epitomized by the fact that we, in many of these buildings, could not turn on the lights again for several weeks, in some cases several months. And so I'm going to talk about this whole issue of human security and living system security. Why are we motivated to fabricate? Why are we motivated to build? And what are the criteria that we infuse into our built environment systems? I'm going to look across. As Meta said, we sort of try to piggyback as much as we can off a lot of building projects, large and small, and we're also principals informing criteria at the schematic phase design on exactly how to organize buildings for sustainability, if you will, or biocompatibility, however you put it. But I'll focus here on just a few research areas, and I'm going to focus on 3 principal buildings, one in Botswana, another one in Nairobi, and another one in New York City, in the Bronx, and looking at that. And also I was really humbled, when I was invited to do this. It was really incredible invitation for me, because it really made me also reflect on some of the sort of really key philosophies or publications that really sort of set us in motion. This is a publication in 2004 called Versioning, and the actual article is called Recombinant Assemblies, and it's just as relevant to us as it was then. The cover of Versioning shows what we consider to be maybe, I don't know if it's the first one, but one of the first model-based deliveries of a built environment of shop architects, PS1 MoMA, and it was just like small 2x2s. Of wood, but it basically was one where they just set, the sort of drawing and conceiving of buildings as usual was sort of over. Now we see that Shop and many others are delivering massive district scale installations of built environment with model-based delivery, and it's quite inspiring and incredible how much they're able to optimize and sort of tailor the process. And yet at the same time, I still look at this old picture of a Bidarka kayak that is thousands of years of tradition of basically understanding the interface between biological materials and the aleatory complex environment, in this case of waves and wind and all sorts of forces, whereby they are placing in a design for disassembly and foldable kayak at the most incredibly inflected points. Where does certain level of flexibility of bone and other types of materials have to be placed? And if we would compare that to the most high-tech, quote-unquote, carbon fiber kayak, we can see that there's no comparison in the performance on multiple levels. So having sort of set that sort of framework, I'm just to ask the question, why fabricate? What is our motivation, and at what scale do we want to fabricate, and why does scale matter so much to us? We're obsessed with scale at Yale CEA, and the first type of system I'm going to be, or premise I'm going to be showing is looking at how we integrate scales with assembly logics with 20th century technologies. So this is IC solar facade, where it's considered to be much more, it's combined heat and power, for example, at over 70%, right? And it's designed for disassembly and reassembly, and it uses less than 1% semiconductor in comparison to systems. It lowers the building cooling loads and the lighting loads, et cetera. So it's got all this criteria associated with it, and yet it is still, in a sense, in that mindset of receiving materials that we developed at different single scales and single functions and assembling them, putting them together. And still, we might be able to do much more than we're doing today with assembly logics. Our computers have assembly logics. Many much more advanced fields than ours have assembly logics. But then for us, we also then start to think, okay, what if we, in a near term, so this is how we're basically looking at parallel tracking near term with midterm with far term technological possibilities. What I just showed you is using everything that we can with semiconductor and optics in our own world now that we have, and then we start thinking, can we be pragmatic and hybridize, have these kind of biomechanical Frankensteins, we call them, where we place biologicals into a framework that could be conventional and could be received. Why do we want to do that? Because we're actually, even though I'm going to show you a lot of fundamental research today where we're really projecting into a kind of brave new world, a completely new way of doing it, we're also very interested in getting some of these technologies into buildings right away. And so this is an example of the sewer technology that we're going to show tomorrow, where there's an interface between biologicals coming from humans and all sorts of other contaminants in our environment, and plant-based photosensitizers, where we're leveraging basically just our own biology and that of the ambient environment to sterilize water and reduce the sterilization time from 11 hours, which is current solar technology, to 6 hours to 11 minutes, rather. So roughly, those are the rough ballpark, preliminary findings. So it's really about, in a sense, we've been accused of being solutionist and all of these things. Of course, yes, we're really interested in problems, and we're interested in getting busy with the solution of problems. So we will say that does drive us, and we'll say it earnestly as well. And then also, of course, thinking about what are all the biomass flows in the world. If we were actually to see the biomass flows in the world and how much of this agricultural waste we're producing, this just happens to be a map of the Global South, how could we potentially recycle and recirculate that into productive material economies? Lastly, then, I'm going to be talking about these kind of super high-tech ways of manipulating energy and water and materials that we're discovering that are emerging in the informatic and biotechnological and nanotechnological revolution that we're living. And talk about why, even if most of what we have in built environment is already built, let's say in the global north or here in Copenhagen would be an example, we're still building, as was said this morning. We still build, and we still need to retrofit, and we still need to convert and transform. So how are we going to do that, and why are we interested in that subatomic scale? Why would architects get involved in the formation of criteria at the subatomic, meaning at the unseen scale of how materials behave? And why would we not just leave the development criteria of the emerging materials that will be protagonists in the 21st century to scientists or engineers or let's say industry? Why should artists and architects be involved? And conversely, I'll use the same question about why do biologists, ecologists, sociologists, chemists, and so many others need to really be part of our teams at the inception of the formation of criteria, not grabbing things, or being inspired. Those are all important. Designers need to be inspired, and they look at all sorts of things. But why do we need to actually talk it through even before we put pen to paper, let's say, or type out on our computers? In the natural world, as we can see, we have very complex geometry across all the scales, right? And this is an image of the power. It's just a still from the powers of 10, Charles and Ray Ames in the mid-20th century. And I would say that we're in a sense, a kind of parallel moment right now. We're heading towards the mid-21st century. What was the euphoria in the mid-20th century was that we could actually visualize all the way out, all the way down into DNA, understand what does that look like, how is it formed, how is it changed, and then zoom out all the way to, let's say, stratosphere, but let's just start with our atmosphere. In the formation of the atmosphere, in the geometry of our aerobiome, for example, that has a concomitant effect, an interdependent effect on the geometry of the DNA, as we all know now. So we are completely interdependent, and natural systems have interdependent geometries that are extremely complex, and that we know very little about, actually. Just as an example, we still don't even know how to reproduce photosynthesis artificially. So where's our oxygen coming from right now? It's coming from plants, and plants can do it much better than we can. We can't even do it. So the other thing about all of this is that if we are going to zoom down into these really subatomic scales, how do we visualize that, and why is it so important, in a sense, for that to be collective and immersive visualization? So we're very interested. I'm sorry these are not working, these videos, but this is basically looking at a condition where we have multiple different types of interdisciplinary folks in a room, from biomedical engineers to facade engineers, computer scientists, et cetera, all embedding criteria into how dynamic layers, let's say, you could just even think of a ceramic frit that was movable or dynamic. How are all these things behaving? And how do we want them to behave? So when we have a lot of different people embedding criteria, what is the outcome? And how do we democratize that process, and how do we make it Yeah, okay. So the other reason why we need to look at multiple scales simultaneously and actually start to design, co-design, in a sense, with living systems is because we have very complex responsiveness. If we want to be bio-responsive, if we want to be net zero or whatever the buzz terms of the moment are, if we want to ultimately be able to move with natural rhythms, I think the UN uses the term nature-based processes, then we ultimately need to be moving also with nature. So we need to understand at what scale and in what way would things be responsive. And another thing that is super, super important to us that I will say, and this is probably the key point, is that on the left-hand side of this image, as we go all the way down to the subatomic scale, we literally have multiple handles on the energy. What that means is that at this is at micro scale, where let's say we put a ceramic frit or we put a low E glazing or we put something else on our window or our surface or a nano paint, what you see is what you get. Unless you're starting to actually manipulate the energy flows all the way down to subatomic. But we can disassociate. So what you see is what you get here in the sense that maybe all three of these patterns have the same performance values. So we can see that, but we will be associating the performance value with the pattern that is on that facade. So we can see that these patterns, for example, if you could think about them as shading, or you could think about them as ceramic frit or electroactive polymers, whatever material, if it's at the micro scale, we're going to see what it is, and it will change our view, and it will be a permanent condition. At the subatomic, we can change it, and we can disassociate what you see from how it's behaving. And that is why you can now see, let's say these are all, in this case, 2D carbon nanotube layers. It could be graphene layer, or it could be another type of nanoscale. What you're seeing there is that we could embed, let's say, a social criteria might be a patrimony, a pattern, contextualization, privacy, whatever. There could be all sorts of social. There could be, obviously, a lot of economic criteria. There can be environmental, there can be life cycle criteria. But how do all of these criteria start to embed and interface with each other, potentially in layers that are invisible? But many, many more layers. We're not stuck, once again, with that macro behavior. And I mentioned this issue of immersion, why it's so important that we have new types of visualizations and visualization methods now if we are going to, and I'm going to say that the 21st century power of 10, I would posit, is basically being able to design in multiple scales and from multiple points of view, potentially. Now, the big danger of this, of course, is this becomes a multiscalar black box process that can, in many ways, through artificial intelligence, we can trace, and we can trace provenance, and we can start to understand. But really, the majority of these processes in this early phase are not traceable. So we don't really know exactly why certain behaviors are emerging. And so even more than before, we need socially embedded criteria, and we need discursive criteria where we are inside, literally, the molecules. We are inside these structures that we're creating, and that we can basically zoom down and zoom out together. And that's a very, very different thing than virtual reality, of course, where virtual reality, I would posit, is a very important tool, but it's still semantically, on a semantic level, it's projective. It's individual. And so what we're really trying to get at Yale CE is how do we get these tools that are social? And how do we follow the thread between the criteria? So I'm just going to... So it may seem that all of that is, super abstract and out on Mars somewhere. But actually, the kinds of test beds that we are choosing increasingly are extremely modest. Meta mentioned ecological living module. This was the first ecological living module that we were invited by the UN Environment Program to demonstrate, and basically they said, we want you to show us on the plaza in New York City, what could you do with net zero? net zero energy, let's say. And we said, well, you know, net zero energy on its own really doesn't make a lot of sense. We had 2 months, and then we had 3 days to install. This is a little fabrication fun story, and we could not touch or screw into the plaza. We had to be resting on the plaza. So what did we do? We brought a bunch of materials that are very typical to the northeast of the United States, which is, you know, timber, TLC, CLT, et cetera. And we grabbed a bunch of the systems that we already had in our labs, put it all together into what is essentially at 20 square meters, believe it or not, this is the scale of a refugee module for UN High Commissioner of Refugees. And you know, in the context of Gaza and in the context of so many places around the world, we can say the median time to live in a refugee module in UN camps is 18 years. It would be much longer in places like Gaza, several generations, of course. And so how do you provide for that feeling of commodity and human security in the context of that? Clearly, you know, wood makes a lot of sense in the Northeast United States. It might not make any sense somewhere else. So we'll show something completely different in Nairobi, for example. But things might be a lot simpler in different ways if we didn't put labels on them. And that's where I would like to say is that for us, you know, we're just as happy with a car jack and a low heat press and some agricultural waste and some binders as let's say, you know, cultivating crystals on graphene nanofilms. Whatever makes sense in the context, we think that in a sense we should put the sort of behavioral criteria around it rather than labeling one material or another material or sort of fetishizing a process or a designation. So I would say that we work with all of the materials potentially, but we do have criteria that lead us in certain directions. And so for this module, what we did demonstrate was, we said it's important that we have net zero energy, water, air quality materials, and we need to show this through food growing plants. This is, if you want us to do this, is what we'll do. We'll show you how we would leverage building integrated agricultural systems or you know, farm walls, basically, in this case, to deliver that. And so before I go further, I'm just going to do a little also shout out to our presentation tomorrow, Monty Pretorius, and we're going to be there for questions, to just show in the context of a completely different ecosystem before we go on with New York, to show that, you know, in the context, let's say, of South Africa, Cape Town, which went to, was just several days away from net zero water, or sorry, 0-day water for a city of 4 million people, over 4 million people, and that was just a few years ago. This is a temperate arid climate, right? So we're talking about something completely different. But we can see also what really motivated us an ecological living module to look at some of these smallest units was both that sort of proximity of human bodies, plants, extended ecosystems flowing through, and you can see the disparity here in the access to resources. This is a citywide water map where they were literally outing people using too much water, according to the sort of requirement to reduce, but we can see this difference between the informal in the middle and the formal housing in terms of access to all sorts of ecosystems, resources of green and water table, et cetera. And so what we're going to show tomorrow with Sur is just with these very, very common plants. This is a biochemistry, the extracts and the photocatalysis, that basically in association then with the rhythms, and there's a very, very important aspect of time, as I said, and movement through the system. And in the article in FABRICATE, we also do allude to the hydrogel area where we are, the drips area where we combine with the sterilization, the collection and purification of water, and then the sterilization of that with the absorption from the ambient. So that, and that's what we did actually, and we needed to do that in New York City as well because there wasn't enough ambient falling right on the roof of the system. So looking at, for example, planting aquaculture waste from fishing, and looking at the sort of extended local ecosystem. How do we put all of those waste byproducts together into a system in order to both sorb and sterilize the water? In the case of New York, we needed a pre-filtration because also the ambient water coming down, the rainwater was so polluted. So there was a pre-filtration through this plant wall that is also reforming VOC's molecules through an engineered growing media. So, and I'll show a little bit about that towards the end. So you have basically an ecosystemic approach to the entire thing. And Mondi will explain more about the system. And of course, the data that we are interested in is the living systems data. We take it from ourselves, from the humans, and the other living systems in the space, and we measure how we're doing by the relationship between humans and these systems. And I think that one of the most important and exciting findings we found is even in what we call young and dumb bodies, meaning young bodies are often not the best measuring stick because they don't always respond too badly to stress. But we did find actually that within 1 hour of tests where subjects that were 20-something student subjects that did not know plants were part of the study, we could see biostatistically significant changes in heart rate variability and in breathing rates. So this is really amazing to see that our connection to non-human living systems is so intimate, and we've co-evolved over millions of years with these systems that when we're separating ourselves from those systems, all sorts of things are happening that we're just finding out in the biodiversity hypothesis, not least that you have basically very low biodiversity or human biodiversity. So the system that I'm going to focus on right now with respect to scale is this system that I just showed, IC solar facade system, where it is a system that is we try to move things out of the university as quick as possible. The mandate from CASE and our partners at Skidmore, Owings & Merrill, SOM in New York, was always that we would basically accelerate the deployment of game-changing technologies from the lab into actual building projects. So we're not interested in commercializing our work, although many of our students have, as I'll show you in a minute, including the mycelia that is being used next door. We have a lot of, but the licensees, Helioptics, were interested in district-scale solar. They were interested in the fact that we were developing something that could potentially lead towards district scale and DC microgrid self-sufficiency. And so the first large-scale district building that we interfaced with is the Botswana Innovation Hub in Botswana, obviously not far from the airport, and you can see it's a savanna ecology, where we collaborated very closely with the architects in developing the floor plate and morphologies and the savanna ecology to go underneath and on top as much as possible with this, with an energy and water blanket that would first of all try to, as much as possible, preserve the flora and fauna. So old growth trees were all completely off limits, and the entire floor plate and massing of the system was meant to be built all the way around it. But you can see in the distance there all of those clerestory windows that are along, and those are the windows. Botswana is fairly far south. It's just north of South Africa where we were. So it's almost the same as New York, but on the southern hemisphere. And so those are facing north, and they're quite vertical. And those are the solar facade windows there. And I'd also like to just mention, because this is also related to we use this as an example in the global report, not for solar actually, but we used it for circular concrete, because there is, for example, in a building like this, a lot of concrete. But we think that this is a very good example from partners. We were not involved in the design and development of these concrete modules, but it was shop architects, Bureau Happel and Spirol, who were looking at the optimization and reduction of material by optimizing the systems within the concrete modules, complete on-site factory-based delivery, electrified, not by renewables, unfortunately, but a good start to basically reduce transportation, reduce all sorts of different ecosystemic problems with environmental impacts of concrete with that. And it is as circular as probably many examples are as far as it goes. It's probably being designed to be in place for as long as possible. But here you can see that the solar was the connection, to the outdoors, because, sorry, what we didn't see in that savanna environment is that in a hot, arid climate, also daylighting is a big problem because of the contrast ratio and all of the diffusion in sort of the particulates in the air. It's a very sort of dusty climate, and so this is really quite an old drawing. I mean, this is probably 20 years old now at this point, but the criteria for what we're trying to do is very similar when we go all the way down to the nanoscale in a minute, as we'll show, is that ultimately we're interested in transitioning building envelopes from barrier conditions or sort of non-responsive conditions to transfer functions, or ways to basically absorb, capture, or redistribute energy. You can think of one of the first things probably in first wave sustainable design that they tell you, shade, offload energy, especially in a urban heat island. Well, we would beg kind of what we thought was an obvious question, which is, where's that energy going? And just sinking into the pavement in front of you. If you're going to offload energy, how are you getting to net zero? So all of these dictates of how we're going to move towards sustainability did not add up very well with that first wave of recommendations of how we're going to actually, interface with the built environment. But here, as we're seeing, we're sort of ending with the end uses, right? And once again, everything's on a clock. Everything is bioresponsive. Here's another building by Shop, the Fashion Institute of Technology, which is a retrofit building. On the bottom, you can see the original building and a south-facing facade into an atria, where this would be the only daylighting for the entire student body and their student union, and you could see those New York canyons, how little daylighting is down there. So grabbing that daylight and then also trying to really power, in this case, as much of the emergency lights and as possible. So what are we doing in sort of 20th century technologies, or our kind of typical technologies that we see all around us? We're basically, this is just a view of the of all of the different scales, the morphologies in that system that you just showed. We have, I'll take you through it, but basically from optics to semiconductor, all the way down to the cultivation of crystals. But ultimately, they're not interdependent like what we saw in the bio, are they? Right? So we've got a tremendous way to go, and we have to be very, very humble in the face of biologicals and what they're really doing. But ultimately, and I don't know if you can see this, it's quite bright here. I mean, we could turn off the lights here if it's hard to see. But basically, at that sort of ergonomic scale, sometimes we call it the ugly scale. This is a scale we see. We were very excited initially to be able to shade with transparency and interface and track. That was kind of, it's still big news in a way in comparison to a lot of our conventional technologies, but it's not necessarily news today that, moving systems are not that difficult. They were in the beginning, but largely because of, we were mostly an on-site fabrication type of discipline and many things. The famous ones, maybe I'll out them. The Jean Nouvel, l'Institut du Monde Arabe is a good example of many moving systems in the beginning sort of not working after a few runs. And a lot of that had to do with tolerances, and it had to do with the way that we were specifying buildings and making and interfacing with manufacturers. We no longer have those issues. But one of the things that we do have is we embed a tremendous amount of embodied energy and non-renewable resources now in our so-called smart buildings. And for example, just for the semiconductor and the microelectronics, we have to go to 1100 C and back within seconds to make those morphologies. So the smaller we go down in scale, the more embodied energy we are putting into our buildings. This is getting now into, once again, we can see the direct transition from the earliest forms of making. We're just carving into molds, in this case probably metal, to make a compression mold out of plastic with optics. We could make it with stickers or other things that are more high-tech, but in general, this is the kind of conventional way of making optics. Then in the semiconductor, we have all sorts of complexity that we have to render, and then the relationship. And then once we start getting down into this very interesting scale, then it's all interesting, but it's very interesting at this scale that we start to have switchability, and we start to be able to grow basically the morphology that we're looking for and the behaviors that we're looking for. So looking at that, and then I'm just going to take us back out, to the scale that we're sort of used to sort of visualizing in, and remember that what the context of this, we all the way from, if we think about, let's say, this being an ecological living module, we just showed a very, very small self-containing module. But if we look at the context of, let's say, super high density buildings, we have a very, very limited amount of interface with the bioclimatic resource, the more dense we go, right? And so this is a really, really important principle is our surfaces, we could count and beam count literally millimeters, square millimeters, in terms of what we would do with them, in terms of an absorption, transformation, conversion, and redistribution of the energy. So ironically, in this luxury condominium in Busan, we have less access to bioclimatic resources than we do in the tiny ELM from that standpoint. So I think that that's also, why do I bring this up, is because I think that in the future, we're sort of once again at the very beginning of ecological economics, where we have carbon accounting, we have offsets, we have carbon taxes. We will also start to be looking at our resources very, very differently in the codes and in the building codes than we do now. So the question is, what is the access, let's say, to the power of on-site net zero and to the power of bioclimatic resources? Yeah, and just, so this is a very early set of modules, probably about 20 years ago. And then I'm also going to completely switch gears to say that with this system, all of this manipulation of geometry that you see here in these graphene layers, we have the exact same criteria. In fact, we have more criteria in these layers than we had in that system that you just saw with all of those single function materials. In the graphene, we're not just trying to maximally absorb, convert to energy, convert to electrical, change the daylighting. In this case, we can disassociate, for example, the visible transmission from the solar heat gain coefficient, so that we're not literally needing to even think about whether it's transparent or not relative to the functions. And so all of those different functions that we have get, in a sense, manipulated and designed at that in a sense, unseen scale. And that's the surface, right? That's the surface of what we have. So none of this morphology and the relationship between all of that morphology, there's just a bunch of, if you're interested in the scientific reviews, there's a lot on our website. But we will obviously still need bulk materials. So what is that relationship between those incredibly intelligent surfaces that I will say are not low energy, obviously? We still don't know really how. Maybe we can cultivate the graphene to do all of those different things, but we don't know how to scale up in a way that is very low energy just yet. But let's say we will always still be building in bulk materials, and we will always still be having a kind of necessity to inhabit a terrain. And so this is where, in a sense, I'm kind of maybe recalling some of the stuff we saw earlier today. Here, this is a 3D printed pavilion in Nairobi. It came via Miami. Its first stop was in Miami at Art Basel. And so it spent 2 hurricane seasons in Art Basel before it came to this. So you can see that it's holding up very, very well. The principal structure was of bamboo, and a number of different binders that were experimented with, which I cannot talk about, but I'll talk about binding in a second. And the partners on this, for example, are Shop Architects. And for the 3D printing branch, Technologies was printing the carbon fiber baskets.
And Oak Ridge National Labs was printing the post-waste bamboo, the bamboo detritus, and there are many other partners such as Willow Technologies, Ecovative, Fabs, and Mimic, who I will mention in a minute. I think this is not my last PowerPoint that I submitted, so some of these, I apologize for some of the credits, but I'll talk about the deployment context and how we are basically making. So our interest, believe it or not here, is that we are taking these substrates that, for us, 3D printing is very interesting if it inverts, let's say, a material economy. So we were particularly interested with our partners in East Africa and other places in the possibility that you could have 3D printers on the side of farms, that the 3D printer could make the 3D printer, that it could be run by solar, et cetera, that all the things that you need in a conventional factory process, like, and all the things that cost a lot of money, like space, labor, energy, other inputs, material inputs, might actually be not only available, but might actually be positive plus inputs, like, for example, the waste that you have to burn that then puts carbon up. That if you can take that waste and not burn it, or take the forest floor detritus byproduct and not burn it or let it decay into emissions, then that gives you carbon offsets before you even get started. So, what do we have a lot on farms and in forests? We have time and we have space, and sometimes we might have a lot of energy and a lot of materials handled properly. So, but what you're seeing here with our colleague from University of Nairobi is you're seeing that he's actually sitting on a bench that's delivering coolth or heat on demand from solar. Because basically what we're doing is we're embedding within that material and within that bench a thermoelectric. And now that thermoelectric, I don't unfortunately have the logo of Mimic, but check it out, Mimic, M-I-M-I-K, is Berardo Mattalucci, one of our former PhD students and head of research design at SHOP, who is carrying that technology forward and developing it into new material technologies. But one of the things that you can see here that's really important about this climate is it's completely different from New York. We're completely outside here. It's a climate that is a temperate climate. Nairobi is one of the greenest cities in the world, as you saw from those earlier videos. And the last thing they would want to do is cut down the trees, the old growth. They have like millions of people living under beautiful old growth canopies, even in and around peri-urban environments. So the question is, in what way would we deliver biomaterials or circular material economy to a condition like this? And with the branch technologies, they happened to be interested in carbon fiber at the time. I think this was the largest 3D printer in the world at the time, is over 10 years ago. But we were personally interested in the idea, so we were parallel tracking with the carbon fiber, using that as a baseline of one of the strongest, let's say, prints that we could compare our agricultural detritus, where we could grow, we could print to grow basically, and to create a scaffolding for all sorts of different other things to happen. And then here, this is Willow Technologies. This is actually the PhD and undergraduate studio modules, and Mailing Loco, who founded Willow Technologies, is the founding CEO in Accra, Ghana, off of her PhD work in this area. This is literally looking at the kind of mycelia you see next door. Actually, we used that in this panel. But this is, I hope I do have, this is, oh good, okay, and these are full mycelia acoustical panels. But I want to just say a little bit of a note about this. Here is Ecovative. It's our students, Eben and Gavin, were undergraduates in product design and innovation at RPI, and we were devastated that they didn't do the PhD at CASE 20 years ago. Instead, they founded Ecovative. But what they now have is over 300 recipes from around that are used around the world, including what I saw next door, of cultivating mycelia from all sorts of things, from a candy wrapper, to many different things. Initially, they were thinking about this as an insulating material inside that what we call, these kind of fluffy bricks, if you will. These we were interested in what you could carry on the back of a bike or just be very, lightweight, et cetera. But ultimately, there's all sorts of difficulties, as I said, with bringing agricultural processes into a throughput 20th century factory framework. And ultimately, we might learn a lot through other industries like the beauty industry or the textile industry, high-end textile industry, about mycelia and how to grow textiles and from food and other stuff that might come back to the building industry. But I think it's very important, and I'm excited to see that people are so interested in all these materials, but I think it's super important that we keep our eye on the ball as to what we're really looking for in a lot of these materials, what is interesting about them. In this case, they do provide tremendous structure to the coconut prints and to the soy binders that were used in those. But ultimately, they're very expensive processes. So how can we start to think about looking at our built environment and aligning the production of our built environment along agricultural cycles and along forest growing cycles? So that's one of the things that you will see on our website if you're interested in looking at further. How are we interested in embedding the geometries and growing the geometries into these materials, and also allowing for the time and space that natural growing cycles make? So this is also 2008. It was big news that we could use plants to design, our air conditioning systems. It's not news anymore, but it's still super early days. And I'm just showing all of these different venues because I'm super fascinated at the discussion here at FABRICATE, that it travels across art and science and engineering, and it's so rare to have this discussion. And so we would keep things all separate. We would submit to MoMA for this bio design, for example, or we submit to the next one, I think, is or the advanced materials, or whatever the different venues are, and keep our disciplinary P's and Q's kind of straight and acceptable. And I think that we need to bust out of that. We need to create space, and we need to create space for seeing the world differently and recognizing that the venues for publication need to be a lot more like FABRICATE. They need to be a lot more inclusive of all of the different streams and ways of thinking and ways of looking at the world. I'm going to just very quickly end with a project in New York City, just to show how we're kind of constantly going back and forth from the straitjacket, let's say, of modernity and the modern world, and then into the bio world, and then and try to, it's this kind of Frankenstein, the dance, we call it the Rite of Frankenstein. We're sort of like trying to create a dance with modernity and see, are there hybrids, are there messy hybrids that might actually reveal something important about what we can do with our cities and our environments today. And so here you have, of course, it's the map from NASA Goddard Flight Center, and it's called Global Light Pollution. How can we see this, maybe in the Anthropocene that we've inherited, a little bit differently? We were fascinated by the fact that all of these lights are on all evening, night, whatever, and they're supposed to be for humans, but they're not really for humans, and because a lot of humans are sleeping, or should be sleeping, or can't sleep because of the light pollution. How could we think about those environments very differently? How could we start to think about them even as opportunities? In this case, for nighttime photosynthesis and for the production of fresh air from within buildings. We live in a world where, unfortunately, the majority of large global cities have catastrophic air quality, and it's projected to get very much worse in the coming decades, sadly. But we also have plummeting oxygen levels and rising CO2 levels that are disproportionately rising in global megacities. And there's an opportunity here. If you saw where we were with ecological living modules, already in the era of urban agriculture. New York City is a good example of where urban agriculture has actually exploded, and now it's even sort of viable, you know, in competition with a lot of other forms of agriculture. So we have ways of thinking about our relationship to food and to sustenance and security and flows really differently. And so this is an example where we leveraged our partnership, the AEC partnership with, in this case, Skidmore, Owings and Merrill. Depending on your predilection, you might see this as a giant Donald Judd sculpture. It's impeccably detailed, it's beautiful in many ways. But it's kind of the antithesis, obviously, of open ecologies or integrated ecosystems. This would probably be one of the buildings that we would say is the most closed loop ecology that we could imagine. So the opposite, in a way, of what we're saying. And we were, even, this is like obviously ironic, the criteria that we leveraged to be able to use this as an incredible site of research is that it has, like many embassies and corporations and high security buildings, post 9/11, it has a programmatic requirement of having to shut off the fresh air intake in case of a Fukushima, a bioterror attack, a 9/11, et cetera. And it's usually a trick question, but I know we're running out of time, so I'll just say, really, the max you can survive in this building if the fresh air is shut off is 10 days. So you can imagine after a Fukushima, we have Indian Point, which is a large nuclear facility just north of New York, which they closed it, now they're thinking of opening it again and all this stuff. So it's just completely possible, right, that we would need to have this public safety answering center for Greater New York. The first one was underneath the towers that went down, and so this is a redundant center. It's the second center. And it has this rhetoric of safety. So we said to the Bloomberg administration at the time, we said, hey, come on, what happens after 10 days? Why don't you let us create a safe zone within a zone and test the potential to produce fresh air from within this building? And so we, with our 5 other university partners, actually Cornell is one of our university partners, Weill Cornell Medical School, NYU, Columbia Earth Observatory, and Columbia Lamont Earth Observatory, RPI, my former alma mater, and of course Yale is leading this research project, and we're looking at basically, so the architecture is what it is, but we have this large-scale bio wall. Even actually the design ended up being, in a sense, straitjacketed into this building, as we'll show in a minute. Here's just a gathering of some of the scientists that we've been collaborating with from Columbia and NYU and others. And looking at basically, are we able to produce net biodiversity? Could we create forest bathing within, let's say, a building such as this? Could we create a condition where we could lower stress levels, where we could lower cortisol, where we could create what we call yogurt for buildings, basically a probiotic condition? Now, sometimes it gets a little bit hairy because people mistake our research projects for designs. That design that you saw just now is an instrument. It's an instrument for measuring, ultimately, more than it is really an architectural system. So I think, and same thing in a way with the Nairobi Pavilion that I just showed. In many ways, you know, this is a type of pavilion, but inside a very large building. And we have, and also I should just say, as we're doing this, we're very fond of testing on ourselves. So this is a picture in the lobby of SOM with one of our PhD students who's basically testing a standalone unit that goes all over into multiple spaces and environments. And at the time, we were collaborating very closely with NASA on this one as well, the Schoen group. Schoen was the inventor of minimal surfaces. He basically was the first to understand the mathematics of soap bubbles and living systems, and there's been also obviously so much inspiration for everything from artists to architects have really been using a lot of his geometries. And we were very inspired by Bill Wolverton from the NASA Biome, who we worked very closely with. He's a biologist in Schoen's group, to basically develop a lot of different types of morphologies that would retrofit into the existing buildings that SOM and Shop and others were designing and or had already built. And really look at that from the standpoint of microbial diversity, the aerobiome, different species that we could cultivate, including mycelia, so the relationship between the growing, let's say, and the engineering of a growing media, and then the concomitant relationships across all the different scales was, the sort of goal. It remains the goal of the research. And actually, I'd love to invite all of you to attend a dissertation. We'll send that, hopefully, if that gets circulated, of one of our PhD students who is defending Phoebe Mankiewicz in this area. And this is some of her very early experiments here at Case in the sardine can, and looking at, once again, those interrelated morphologies between scales. I'm not going to have time to actually go to the last project, but I will just say that that issue of interdependency in the development of ecosystems, in this case, you can see on the top solar collectors that are integrating both IC solar and also some of the nanoscale electroactive polymers and hydrogels sorbing water. In this case, this is a very inhospitable climate where it's 110 degrees in the summertime and very little water, although there's enough water to soar because it's close enough to the coast in the Gulf here. And looking at, one might question the ethics of creating microclimates at this scale. You can see on our website we've collaborated with Bureau Happold and Arab and many other engineering firms around the world with their architecture partners to look at the possibility of multi-scalar massive climate change. This would be a microclimate at the scale of a very large sort of block and district. And so, of course, we are changing. But I would also say, aren't we changing, for example, the microclimates already with our urban heat island effects? Already, like with this, it's a very different way of changing the microclimate. We're absorbing the energy, we're metabolizing it through the system, and we are recreating such that below this, we can create certain bioretention, and we can create, just like we were doing at Botswana, if you saw those interior courtyards, those are literally concentrations of humidity and bioswales, so that when people go outside into those concentrated areas, they actually have a kind of profile. We don't say psychometric profile outside, but they have a kind of amount of humidity and light that is really hospitable. Okay, I only have 2 minutes left, so I would just say immersion's very important. This is one really interesting experiment where the criteria of dozens of people for changing a pattern, a graphene pattern on a window, is leading to all sorts of different biomorphics. This is not working. These are stills from visibles. I think we're over time, right? Okay, thank you so much. I'm going to end there at that, and just to say once again, okay. That's fine. That's good with this. Actually, I think it's hilarious that I ended on this because of this this question of money. These are just disused computers, and what I was going to say with this slide is there's supposed to be there are videos there. We will use any type of disused waste byproduct for research, and we don't get a lot of money, but we are, working through it.
Anna, thank you so much. Stay here.
No, okay.
I know we're over time, but it is unstoppable, and it was such a wonderful fly through of so much of your thinking, and thank you so much for the generosity of wanting to let us into the way that you are thinking about these things. I think it is a wonderful provocation to us at the end of day one that you open up the system boundaries of what our concern is. You ask us not only what are the... Sorry guys, we're just going to keep the focus for 3 minutes more. but that you open up the system boundaries of what we're thinking to wonder about what are the resources that we're trying to conserve. So we've been talking all day about different kinds of material systems, how can we rethink them, where do the resources come from? And I think what's so wonderful about the work that you're presenting is this idea, well, energy, water, food, the way that we act in the world, the environment, the actual aerobiome, as you say, is also part of these resources that our architecture also needs to consider. And how do we do this? I think if I'm allowed to just expand on one thought that you present, and I think this thing that you're saying, well, the 21st century power of 10 is about multiscalar thinking. And I think in our community, we have been so concerned about this over the last decade. We've been thinking about different ways of expanding the digital chain to be able to work not just with given materials, but to address material systems, to define them ourselves through different kinds of robotic or digitally steered methodologies. And I'm just wondering, when you're showing your work here, you're showing such a rich palette of different material systems. And I wonder if you could think about a little bit about the transferability of that interscalar or multiscalar behavior. Is there something that you can bring with you from one material system to the other, where you're starting to say, well, maybe these are the sort of underpinning methodologies of this 21st century work of design?
Yeah, that's a great question, because actually on the last one that I was going to show a ceramic, where there's morphology and surface characteristics and surfacing that might pertain to any material potentially. But the question is, what does the material, in a sense, want to be? I mean, we don't start with the material, believe it or not. My former center was called Material Lab, and SOM asked me to come in and do materials research because the materials are so present there. But ultimately, we're always starting with the verbs, with the behaviors. Like, what is the behavior that you're looking to see? And a lot of times, behaviors are transferable for sure. Not always, though. For example, ceramic is a mineral-based material, if a grown material if its morphology is left intact, like let's say a dimensional lumber, for example, what is the transferability of the lesson there? Thanks for asking that question. You know what? I think things are very particular. I actually think that there is transferability sometimes and not always. And I think also that there's not always transferability across scale. I think that's our lesson, is that we don't necessarily want to do the same things across scales. We want to actually be very, very sensitive to the behaviors at each scale, which is, I'm already thinking I would have another lecture for that, but thank you.
But maybe I can ask if I think we have you tomorrow also. I think energy is out of the room, but if there's someone here who really wants to ask a question, then I feel that we should also have time for that and make space now. Okay, then in that case...
Friday night.
Yeah, it's Friday night. So thank you very, very much. Looking forward to seeing you tomorrow. It'll be wonderful.
It was the wrong.
No, it's so good.
Nobody was the wrong.